Welcome to Tomorrow Unveiled.
In the relentless march of human expansion into space, you get weeks that feel like a slow, steady climb. And then you get weeks that feel like a sudden, massive leap forward.
And the period from November 26th to December 3rd, 2025 was definitely one of the latter.
Oh, absolutely. It really felt like an inflection point. It's where all the theoretical dangers of operating in orbit and the sheer overwhelming scale of commercial ambition, they just crashed right into one another.
That is exactly the dynamic captured across all the data our dedicated research team has been compiling. We literally saw a high-stakes, real-time orbital crisis unfold. Kind of danger everyone talks about, but you rarely see happen so immediately.
And at the same time, you have major global powers like Europe committing these historic, almost defensive budgets to try and achieve strategic independence in space.
Yeah, if you had any doubt that space is fully matured into an industrialized, contested, and deeply strategic domain, this past week should put that to rest.
It should. So our mission today for Tomorrow Unveiled is to really distill the core consensus from this huge data set. We're going to focus on three defining global trends.
First, the relentless acceleration of commercial launch.
Yeah.
Then, the immediate, and I mean immediate, necessity of orbital resilience, which we saw in action.
And finally, the really big strategic pivots being made by major space agencies around the world. It's a major shift in thinking.
Here for you, the learner, we have some phenomenal aha moments lined up.
Mhm.
We're going to walk you through the minute-by-minute tension of that dramatic orbital crisis with the Shenzhou crew. An emergency triggered by something so small, it's almost invisible.
Less than a millimeter. It's incredible. We will also fully unpack why the European Space Agency just greenlit a record, what was it, $22.3 billion right in its budget. And this isn't just about funding science. This is a decisive shift in European space policy towards defense and independence.
And to top it all off, we're going to connect a truly surprising data point, the discovery of, well, Martian lightning, and how that directly impacts the safety and the actual engineering for the first human outposts on the Red Planet.
So let's get into it.
We have to begin with the money.
Yeah.
The money and the geopolitical competition, because the investment strategies we're seeing globally are starting to diverge pretty sharply. For years, the U.S. model has relied heavily on the commercial sector, while others, particularly Europe, they've struggled with launch independence.
Well, that struggle seems to be coming to an end. The first major story here is Europe's monumental centralized commitment to its own space future.
And when you say monumental, you really mean it.
Oh, yeah. The commitment made at the ESA Ministerial Council in Bremen is, it's historically significant. Member states finalized a staggering commitment of $22.3 billion over 3 years.
$22.3 billion. How does that compare to, say, previous years?
To put that in perspective, this represents a 32% increase over the previous 3-year funding cycle. It's the largest commitment in the agency's entire 50-year history. This is not incremental. It is absolutely transformational.
That kind of surge funding, it suggests a really dramatic shift in priority, right? It's got to be beyond just scientific curiosity. Why this massive centralized financial pivot right now?
It's fundamentally about two things: technological sovereignty and strategic resilience.
So independence.
Complete independence. For years, Europe has recognized its vulnerability, especially its reliance on, non-European partners for critical launch and for high-capacity communication services. They are drawing a firm line in the sand. They're determined to build out every single piece of the necessary infrastructure themselves.
And what does that infrastructure look like?
We're talking next-generation launch vehicles like Ariane 6, satellite navigation with Galileo, high-speed communications, and in-orbit infrastructure that functions entirely independent of any U.S., Russian, or Chinese assets.
So the goal isn't necessarily to compete with, say, SpaceX on price per kilogram. It's more about guaranteeing access, guaranteeing continuity of service no matter what's happening in global politics.
Exactly. This funding is insurance. It's about making absolutely sure that if a geopolitical crisis were to restrict access to foreign launch sites or communication bandwidth, Europe's critical functions.
Things like banking, military comm.
Everything. Banking, synchronization, military communication, weather forecasting, all of it can continue completely uninterrupted.
And our dedicated research team highlighted that this isn't just a vague goal, right?
Yeah.
The budget breakdown actually mandates this shift.
It does. A major structural component of that $22.3 billion is dedicated to a new initiative, the European Resilience from Space, or ERS. Now, they are still funding core science missions, fantastic stuff like the LISA gravitational wave detector and the Ramses mission to intercept the asteroid Apophis.
But the real money is in this ERS fund.
The sheer size of the ERS fund confirms that space is now officially a strategic domain, one that requires sovereign protection and, critically, what they're calling non-aggressive defense capabilities.
That phrase, non-aggressive defense, is very telling. It raises a question, though. Is this European model of technological sovereignty just a reaction to being sort of locked out of the U.S. commercial market? Or is there a genuine technical benefit to building your own redundant systems from the ground up?
I think it's both, but there is a real technical and strategic benefit. By controlling the entire supply chain from the components made in specific member states all the way to the final operational deployment, they ensure a level of system hardening and security standard that you just might not get when you're outsourcing critical infrastructure.
It's vertical integration, but for national security.
Precisely. And this massive commitment is a fascinating contrast to the strategy we see in the United States. The reports we analyzed noted that while Europe is surging with centralized government funding, NASA is actually facing budget constraints and potential spending cuts.
So they're going in opposite directions.
That divergence really defines the global competition right now. The European path is this massive state-sponsored effort for self-reliance. The American path, on the other hand, is becoming more and more reliant on the blistering pace and, frankly, the cost-effectiveness of its commercial sector.
The U.S. government is acting more like an anchor customer.
An anchor customer and a regulator, yes, not the primary developer of all the new tech. And that bifurcation leads us directly into the incredible commercial velocity being driven by the U.S. heavyweights.
Let's talk about SpaceX, because they're operating at a scale that just defies traditional aerospace models. It's less like a manufacturer, more like a high-cadence, industrialized utility provider.
The volume is just stunning. The research team confirmed that SpaceX maintained an average operational tempo of around 3 Falcon 9 launches per week during this period.
3 a week.
3 a week. It keeps them firmly on track for over 155 Falcon 9 missions completed this year alone. That launch tempo is globally unmatched. It is the highest pace achieved by any single entity in history.
And the Transporter 15 rideshare mission from this week perfectly illustrates that utility model. It wasn't just about the volume of launches, it was the density and diversity of what was on board.
Absolutely. The Falcon 9 that launched Transporter 15 delivered 140 diverse payloads into orbit on November 28th. That mission is the very definition of the democratization of space access. You had major operators like Planet Labs refreshing their daily imaging constellation. You had ICY deploying 5 more synthetic aperture radar satellites,
Which are critical for seeing through clouds day or night.
Exactly. All-weather observation. But maybe more critically, as you mentioned, they also carried orbital logistics providers.
The space tugs.
The space tugs, these orbital transfer vehicles, they represent the essential middle layer of this new space economy. They take all these smaller satellites, which get dropped off in the same general parking orbit by the Falcon 9, and then they use their own efficient propulsion systems to move them into very specific, hyper-precise orbital slots.
It's last-mile delivery.
It's making last-mile delivery and orbital logistics a standard commoditized service. And that is only possible because of reusability. The data this week highlighted a huge engineering milestone on that front.
I saw that. The number of flights on a single booster is getting incredible.
We can't overlook this specific achievement. One of the Falcon 9 boosters used, B1071, successfully completed its 30th flight and subsequent landing.
30th. Wow.
Pushing these fleet leaders to such high flight numbers is the engine of their economic dominance.
Yeah.
Every time they shave off refurbishment time and increase the number of cycles a single booster can endure, they reinforce the argument that reusable architecture is the only way to get to that high-cadence, low-cost access.
So that's the incumbent champion, SpaceX, running at warp speed. But the sources also indicate that the next heavyweight contender, Blue Origin, is hitting a really critical operational phase. They're moving from testing to full production with New Glenn.
That's right. Following the successful NG-2 mission, which not only deployed NASA's Escapade Mars probes, but also, crucially, achieved the successful recovery of the New Glenn first stage Blue Origin, is now fully in aggressive roadmap mode.
So what does that aggressive roadmap look like? What are we talking about in terms of capacity and launch rate?
The company is targeting a massive production ramp-up. They're aiming for a launch cadence of between 12 and 24 missions in 2026.
12 to 24, that's a huge jump.
It's enormous, and this velocity is largely underwritten by Amazon's Project Kuiper. That's a gargantuan low Earth orbit constellation that needs frequent, heavy lift access. By committing to this, New Glenn officially positions itself as the primary high-capacity competitor to the Falcon Heavy for both commercial contracts and, the really critical national security space launch contracts.
And it's not just about LEO for them either. Blue Origin is foundational to NASA's whole plan to get back to the moon.
Exactly. The introduction of their Blue Moon Mk1 robotic lunar lander is a key piece of foundational infrastructure for the Artemis program. This is an enormous logistics vehicle. It's 8 meters tall, has a gross mass of over 21,000 kilograms when it's fully fueled.
And what can it carry to the surface?
It can deliver 3,000 kilograms of cargo to the lunar surface. To give you some context, that's nearly 7 times the mass of the original Apollo lunar module's payload.
7 times. That just shows how much of the logistics challenge for deep space exploration has been industrialized. It's a different world.
Completely.
So while the U.S. heavyweights show this incredible industrial resilience, the week also gave us a sharp, pretty sobering reminder of the sheer technical difficulty of full reusability. And that news came out of China.
Yeah, this was the land-space attempt with their Zhuge 3 reusable rocket. Now, the vehicle successfully reached orbit, which is a significant achievement in itself. It marks China's continued progress in liquid methane-fueled rocketry.
But the landing didn't go as planned.
No. The mission suffered a major failure during the landing phase, which is just incredibly complex. Reports confirmed an abnormal combustion event that resulted in the booster being completely destroyed on impact in the planned landing zone.
So they got the orbital part right, which is hard enough, but the controlled descent and recovery, that's the real hurdle. It underscores that the hardest part isn't getting up. It's getting back down in one piece.
Absolutely. Propulsive landing is arguably the single most difficult feat in modern rocketry. It requires incredibly complex guidance algorithms to navigate re-entry. You need ultra-high-precision engine throttling to manage the speed, and sophisticated thermal management to protect the whole structure. And Landspace had targeted this booster for reuse up to 20 times.
So this failure, what does it tell us about the global race for reusability?
It really validates the years of intense and sometimes pretty painful investment that SpaceX poured into mastering this. It shows that just because you're making rapid progress in getting to orbit, that doesn't eliminate these fundamental engineering hurdles. This technology is not yet a commodity. It requires immense granular technical maturity.
And this whole transition from the difficulty of launch to the necessity of sustained operation, it's a perfect segue. When launch is still this hard, the priority has to shift from just making access cheaper to making the things you already have in orbit last longer, making the whole enterprise more sustainable.
Which brings us to building the future, in orbit and beyond.
Exactly. We're moving now from just the launch competition to the foundational logistics, the specialized capabilities that you need for a truly long-term sustainable presence, the creation of a circular economy in space.
And the concept of in-orbit refueling is absolutely key here. It's transitioning from something that was, a theoretical possibility to a strategic necessity for mission longevity and resilience.
And the market leader in this, Orbit Fab, just secured a major strategic contract from ESA, the European Space Agency.
That's right. Under what they're calling the Astral mission, Orbit Fab secured a crucial contract from ESA and the UK Space Agency. They're going to demonstrate xenon propellant transfer in geostationary orbit by 2028.
And this all hinges on their standardized interface, the RAFTI port.
Yes, the RFTI, or Rapidly Attachable Fluid Transfer Interface.
So I'm a satellite manufacturer. Why do I care about RAFTI? How should you, the listener, think about this standardization? What's the analogy?
The simplest way to think about it is as the USB port for fuel in space. Xenon is the lifeblood of these high-value electric propulsion satellites. We're talking about the most expensive telecommunications and sensitive military assets.
And these satellites usually die not because they break, but because they run out of gas.
Precisely. They run out of propellant for orbital station keeping. So by standardizing this refueling port across all manufacturers, ESA is essentially requiring that all future European assets be serviceable. It extends their life dramatically and enhances the resilience of the entire infrastructure. It's a complete business model transformation based on a standard interface.
Okay, but that only works for the new generation of satellites, the ones designed for it. What about the thousands of older satellites up there that were never designed to be serviced or grappled? That's the legacy market, and that's where Starfish Space is stepping in.
And that is the crucial and, frankly, the terrifying legacy market challenge. Starfish Space confirmed the details for their Otter Pup 2 mission, which is scheduled for mid-2025. And the mission is audacious. They're going to attempt to dock with an unprepared D-orbit satellite carrier.
What does unprepared mean in this context?
It means it has no dedicated grappling fixture, no docking ring, nothing to help you capture it. It's just a smooth, tumbling object.
So how do you grab something that wasn't engineered to be grabbed?
They're using a system called the Nautilus Capture Mechanism, which uses electrostatic adhesion.
Like static cling.
Think of it like a very controlled static charge, yes. They approach a flat surface of the target satellite and use these precise charges to lightly stick to it without all the force you'd need for a mechanical grapple. If this works, it solves a massive problem.
The implication being that it unlocks the ability to service, deorbit, or relocate thousands of these older, unprepared satellites. It could immediately turn space debris mitigation into a commercially viable business.
Precisely. It shifts the entire dynamic from passively hoping debris doesn't hit you to actively managing the legacy clutter that we've created over decades.
And this idea of sustainability, it goes beyond just servicing. It's moving into in-space manufacturing, building the hardware you need in situ, right there in orbit, instead of trying to fold it up like origami and cram it into a rocket.
The necessity of in-space manufacturing is driven by the physics of launch. If you want truly massive structures, like multi-kilowatt solar arrays for big constellations or for deep space habitats, you just can't practically fit them inside current rocket fairings.
You build them up there.
You build them up there. D-Cubed is moving forward with its ARAQYS system, which is designed to manufacture large solar arrays directly in orbit using automated processes.
What's the roadmap for that? And why is that kind of rapid power generation so vital?
D-Cubed is running a multi-mission demonstration program through 2027, basically scaling up to reliable multi-kilowatt arrays.
Yeah.
And that kind of deployable power is significant because it not only serves commercial constellations, but it could also facilitate military applications, things like rapid power generation for directed energy systems, or just replacing critical components very quickly.
And to do all this building and repairing, we're seeing robotics really step up to the plate.
Yeah, the compiled data highlights two key robotic systems. First is IcePark, which is an AI-driven robotic arc welding system. Welding in the vacuum and microgravity of space is a huge technical challenge.
Right, managing the heat, keeping the weld pool from just dispersing everywhere.
Exactly. IcePark tries to solve that with very localized AI-driven process control. And then second, NASA is preparing the Fly Foundational Robots, or FFR mission. That's set to launch a commercial robotic arm by late 2027. This arm will demonstrate dexterous manipulation for on-orbit assembly, refueling, and, crucially, for habitat construction and repair.
So reducing the reliance on humans having to do dangerous spacewalks, EVAs.
That's the goal.
Let's pivot slightly to the security architecture being built around all this new infrastructure.
Yep.
Blue Origin's Blue Ring platform. It's not just an orbital tug. It's being used as a strategic hosting platform for critical surveillance.
Blue Ring is a multi-mission vehicle. It's designed to deliver over 4,000 kilograms of payload and has powerful propulsion for high delta V maneuvers. But its real strategic value comes from its ability to host flexible payloads.
And the partnership we saw confirmed this week with a sensor called Caracal is critical for what's called space domain awareness.
Yes. Blue Origin announced a partnership to host the Caracal sensor on the first Blue Ring mission. Caracal is a high-fidelity optical sensor specifically designed for SDA. That means tracking and characterizing other satellites, including potential adversary assets in both ALEO and GEO.
This really exemplifies the hybrid space architecture we're hearing more about. Commercial platforms hosting military or national security sensors. What's a fundamental strategic shift here?
It creates resilience through distribution and cost efficiency through commercialization. The government moves away from building these massive, dedicated, expensive surveillance satellites. Instead, they just purchase the data from sensors hosted on flexible commercial platforms like Blue Ring.
So the network is distributed, which makes it harder to target.
Much harder for adversaries to target, yes. It provides faster data delivery, and it leverages the private sector's industrial scale for rapid deployment and cost savings. It fundamentally shifts the security architecture in a contested domain.
Okay, so we've covered the intense commercial race, the centralized strategic funding shifts in Europe, and the critical infrastructure being built for this new orbital economy.
Before we delve into the immediate dangers lurking in orbit, and believe me, the threats are just as real and immediate as the opportunities we've just discussed, we want to take a quick moment for our audience.
We've spent countless hours compiling the analysis for Tomorrow Unveiled, and we sincerely appreciate every one of you taking the time to listen. If you're listening on a podcast service like Apple Podcasts or Spotify, we'd be incredibly grateful if you could leave us a rating and review for Tomorrow Unveiled. It truly helps us reach new listeners. Welcome back to Tomorrow Unveiled. We've established that space is now fully industrialized and highly strategic. Now let's talk about the danger zone, starting with a gripping, real-time incident that perfectly illustrates the operational realities of low Earth orbit.
This is the Shenzhou orbital crisis involving the Chinese Tiangong space station. And the incident timeline, which was corroborated extensively across all major geopolitical sources our research team reviewed, is a dramatic demonstration of the lethal reality of space debris.
Take us through that timeline. I want to focus on the sheer absurdity of how small the threat was.
The crisis began in early November. You have the Shenzhou 20 return capsule docked to the Tiangong station, serving as the crew's essential lifeboat. Then, a piece of space debris, estimated to be smaller than 1 millimeter in diameter, struck the capsule's viewport.
Smaller than a millimeter.
Microscopic. But due to the hypervelocity of the impact, this sub-millimeter particle created a penetrating crack. It compromised the structural integrity of the pressure vessel.
So a microscopic grain of paint or a flake of frozen propellant traveling at orbital velocity almost caused a catastrophe. That is the definition of a high-stakes emergency.
It is. Because their primary return vehicle was compromised, the crew had to use the newly arrived Shenzhou 21 spacecraft, the relief crew's vehicle, to return safely on November 14th. This required some complex maneuvers and activating emergency protocols.
But doing that created an immediate serious vulnerability gap. It left the crew still on Tiangong without a dedicated return vehicle. How long were they without that critical lifeboat?
They were left in a vulnerable state for about 11 days, and that is an unacceptable risk margin for any mature human spaceflight program. The response from the Chinese Manned Space Agency, the CMSA, was immediate and highly successful.
This is where they showed their resilience.
Top-tier resilience. They activated their launch-on-need protocol, launching an uncrewed rescue spacecraft, Shenzhou 22, on November 25th. It autonomously docked with Tiangong and restored their full safety and redundancy capability.
So the lesson here is operational maturity. But the crux of the problem remains the size of the threat that started it all. You mentioned the Kessler Gap. Can you explain why we're so vulnerable to this specific size of debris?
The problem is that our current radar networks, like the U.S. Space Surveillance Network, can only reliably track objects that are larger than about 10 centimeters. If an object is bigger than that, we can predict its orbit and we can maneuver our spacecraft around it.
Okay, so you can dodge the big stuff.
You can dodge the big stuff. The Kessler Gap refers to the enormous lethal population of objects that range from about 1 millimeter up to 10 centimeters.
So too small to track, but too big to be stopped by standard shielding.
Exactly. That's the perfect way to put it. Even advanced Whipple shielding, that layered system designed to shatter incoming particles, can be defeated by high-velocity, dense debris in that size range. It's a total blind spot. The Shenzhou incident validates that LEO is increasingly lethal and that we critically need investment in new sensor technology to see these things.
But the dangers aren't just limited to low Earth orbit. The research team highlighted a really significant scientific breakthrough from NASA's Perseverance rover on Mars, which fundamentally changes how we think about the Martian surface.
Yeah, this is the confirmation of electrical discharges, basically miniature lightning in Martian dust devils.
It sounds completely counterintuitive, right? Given how thin and dry the atmosphere is.
Exactly. I mean, we think of lightning as being tied to thick, wet, Earth-like storm clouds. How does this even happen on Mars?
Well, this is a different kind of phenomenon. It's called a triboelectric discharge. It's not your typical water-based lightning. On Mars, the low-density, CO2-rich atmosphere has a huge amount of this pulverized, dry dust. As dust devils churn, these particles collide and rub against each other violently.
And that rubbing builds up static electricity.
A massive amount of static charge. It creates these intense electric fields. And because the Martian atmosphere is so thin, about 1% the density of Earth's, the breakdown voltage is much, much lower.
So it's easier for a spark to jump the gap. Precisely. On Earth, our thick atmosphere is a great insulator. You need a huge potential difference to cause a lightning strike. On Mars, that low-density CO2 atmosphere breaks down much more easily, turning a simple static charge into these dangerous, localized arcs of lightning inside the dust devil. Perseverance actually heard them with its microphone, capturing these distinct crackling sounds.
Wow. And this confirmation has profound engineering implications. How does this change how we design for future Mars missions?
There are three critical interlocking takeaways for anyone designing a human Mars base. First, rotorcraft safety. Future scaled-up helicopters are going to be operating right where these discharges are most prevalent, and the rotor blades themselves generate static charge just by cutting through the air.
So flying through a charged dust devil could fry the electronics.
It's a high-risk zone for a catastrophic electrostatic discharge, or ESD. All future Mars rotorcraft will need much better ESD hardening. Second, habitat grounding. Future human habitats, and especially the big resource processing plants, will act as massive charge collectors during dust storms. They'll need robust, active grounding systems to prevent severe shock hazards to astronauts on spacewalks.
And third,
Atmospheric chemistry. The energy from these discharges breaks chemical bonds in the soil and contributes to the formation of reactive oxidants, specifically perchlorates. Now, perchlorates are a toxic hazard for humans that you have to deal with, but they're also a potential resource. You could potentially break them down for propellant. So the lightning is both a threat and a resource that engineers have to account for.
that changes the design for everything from the airlock filters to the fuel plant. Incredible. Let's shift our focus to the enabling technologies, the deep tech breakthroughs that are going to make all of this long-term high-speed flight possible.
At the top of that list for game-changing tech has to be nuclear thermal propulsion, or NTP. DARPA and NASA's Draco program is now firmly targeting an in-orbit demonstration by 2027. If this works, it's foundational for human expansion into deep space.
We've talked about efficiency before. What is the fundamental advantage of NTP that makes it worth this massive technical and political investment?
It comes down to energy. Chemical rockets are inherently energy limited by the chemical bonds in their propellant. NTP, however, is temperature limited by its reactor core. By using a nuclear reactor to heat liquid hydrogen to extreme temperatures without actually fissioning the hydrogen itself, the DARCO engine is aiming for a specific impulse, or ISP, of around 900 seconds.
900 seconds. That's more than double the efficiency of the best chemical engines we have.
Double the efficiency, which means you need way less propellant mass to get the same change in velocity, the same delta V. This allows for much higher speed maneuvers, which are absolutely critical for rapid transit in cislunar space and for shortening the trip to Mars, which dramatically reduces the crew's exposure to radiation.
But developing and demonstrating a nuclear reactor in orbit, that can't be trivial. What are the key challenges the DIACO team has to overcome before 2027?
The primary challenges are regulatory and technical containment. They have to prove, without a doubt, that the reactor can be launched dormant and only activated once it's in a safe orbit. Technically, the core has to handle those extreme temperatures while staying structurally sound. It's a massive challenge in material science and radiation physics all rolled into one.
And beyond NTP, we're also seeing big strides in high-power electric propulsion, which is more for cargo, right?
Exactly. NASA's work on Hall thrusters is focusing on advanced magnetic shielding. High-power electric thrusters can suffer from channel erosion, where the plasma slowly eats away at the thruster walls, limiting its lifespan. By using robust magnetic shielding, systems like the AEPS for the Lunar Gateway can operate for tens of thousands of hours. That's what lets you move massive amounts of cargo over long periods.
Okay, so let's move from orbit back down into the atmosphere. The sources revealed a landmark finding in hypersonics this week, confirming a really old hypothesis.
This is truly foundational physics validation for aerospace engineers. A study confirmed Morkoven's 60-year-old hypothesis that turbulence behavior remains fundamentally similar in both subsonic and hypersonic flight, all the way up to Mach 6.
Why does confirming a 60-year-old theory suddenly matter so much for modern design?
For decades, the uncertainty about turbulence at extreme speeds, the fear that the physics would just completely change, was a major design constraint. It required massive over-engineering. The confirmation that principles from subsonic knowledge still apply significantly accelerates hypersonic aircraft and missile development.
So engineers can use what they already know, instead of starting from scratch.
Exactly. It leads to faster design cycles for the next generation of hypersonic engines, like the ones being developed for the Angry Tortoise program.
And if you're building reusable rockets that fly 30 times, or deep space habitats, you need materials that can withstand incredible punishment. The sources highlight a huge breakthrough here.
The fatigue-free alloy breakthrough from the Chinese Academy of Sciences is arguably one of the most consequential material science developments of the week. They created a specialized stainless steel alloy that fundamentally defies the traditional trade-off between strength and ductility.
Right, the impossible triangle of metallurgy. If you make something stronger, it usually gets more brittle.
Exactly. They broke this trade-off using a novel processing technique that engineers a gradient of nanite-wind structures within the material. These boundaries act like microscopic shock absorbers. When a tiny crack starts to form, which is the root cause of metal fatigue, the nano-winning structure arrests its propagation and diffuses the energy.
And the performance gain isn't just a little bit better, it's exponential.
The metrics are astounding. The reports indicate this alloy could extend the fatigue life of conventional materials by orders of magnitude. We're talking up to 10,000 times longer under certain conditions.
10,000 times. For a rocket engine like the Raptor or BE-4, that's a game changer for reusability. It could dramatically reduce the cost and time for refurbishment.
And for deep space, you need electronics that don't degrade in the harsh radiation.
That's another huge materials challenge.
Well, researchers identified an exotic quantum state that resists radiation damage. It enables what's called spin-based electronics. Traditional silicon electronics rely on electrical charge, which is highly susceptible to disruption from high-energy radiation. Spin-based electronics, on the other hand, carry information using electron spin. This promises the reliable, long-term function you need for missions to Mars and beyond, where normal electronics just can't survive.
So all these breakthroughs in materials and propulsion enable the hardware. But what about the brains? We're seeing AI move from theory into essential operational capability.
The compiled data confirms AI is being used in multiple critical applications. First, for science observation. There's a new system called dynamic targeting that uses onboard AI to process look-ahead imagery in real time and decide where to aim instruments within seconds.
So it's an efficiency boost. Instead of sending all the raw data back to Earth, the satellite intelligently filters out the cloudy images, the boring terrain, and just sends back the good stuff.
It conserves massive amounts of bandwidth. Then there's autonomous navigation for Mars. NASA engineers flew drones over the Mojave Desert to test algorithms that let future Mars rotorcraft fly over featureless sand dunes.
Because a sand dune doesn't have the distinct landmarks you need for normal visual navigation.
Exactly. The AI has to be capable of recognizing subtle slopes and plotting paths across these uniform surfaces all by itself without constant human oversight.
And finally, AI is now central to national security space operations. The data shows that the NRO's deployment of its new 200-plus satellite constellation is heavily reliant on AI.
This is autonomy as an operational necessity. AI systems are managing the sheer volume of command and control, anomaly response, and orbital tasking for these huge constellations. A human operator simply can't manage that complexity and speed anymore. Autonomy is the only way to scale.
This conversation truly spans the spectrum, from microscopic dust charging on Mars to multi-billion-dollar international budgets defining the future.
We love hearing your thoughts. Whether you're on YouTube or your favorite podcast app, leave a comment and let us know what you think about the future of orbital infrastructure and safety, particularly how we balance commercial ambition with geopolitical resilience.
And for our listeners on YouTube, if you're finding this insightful, please take a moment to like this video, subscribe to Tomorrow Unveiled, and consider hitting that new hype button to help us reach more viewers. And of course, be sure to turn on notifications so you never miss an update on the future. The pace of innovation and just the sheer volume of consequential events from the last 7 days are breathtaking. Let's try to synthesize the 4 core takeaways that really define this new era based on the strong consensus compiled by our dedicated research team.
First, industrialization is maturing. The launch cadence of players like SpaceX, running over 150 missions this year, and Blue Origin's aggressive roadmap for New Glenn confirms that access to orbit is rapidly becoming a commoditized, high-cadence utility service.
Second, resilience is the new priority. The dramatic Shenzhou crisis, triggered by that tiny piece of debris, and ESA's historic budget pivot, both confirm that space is now a contested and dangerous domain. It requires self-reliance and rapid response mechanisms.
Third, the circular economy is coming. The push for in-orbit servicing and manufacturing Orbit Fab's USB port for fuel, Starfish Space tackling the legacy satellite market, these are defining new, sustainable business models for space.
And finally, fourth, deep tech is driving expansion. Fundamental breakthroughs in propulsion like NTP and material science like that fatigue-free alloy, these aren't just small steps. They are the fundamental enablers for the next phase of human presence beyond low Earth orbit.
And these developments set the stage for major near-term inflection points that you should absolutely be watching in the coming months and years.
Keep a close eye out for the Starship operational launches from Cape Canaveral, expected in early to mid-2026. A second launch site for Starship removes a major bottleneck and will just increase the launch cadence even more.
Also, the Dream Chaser Free Flyer demonstration, targeted for late 2026. That will solidify the reusable spaceplane architecture, giving us another option for reliable runway landing access to LEO.
And of course, that DARPA-NASA nuclear thermal propulsion demo in 2027. If that is successful, it could fundamentally reset the timetable for travel between Earth and Mars.
The sources paint this picture of extraordinary progress and massive opportunity, but they also raise a serious, final, provocative thought for you to explore. As commercial companies increasingly take over global logistics and geopolitical tensions, militarize orbit. Who ultimately holds the responsibility and, crucially, the financial burden for policing this newly crowded space environment and mitigating the debris threat we've created?
The ability to get to space is now a utility. The real challenge is staying there safely, sustainably, and securely.
Thank you for joining us for this deep dive on Tomorrow Unveiled.
I'll see you next time on Tomorrow Unveiled.